the topic, vector value functions, where the functions take their values in three-dimensional space. That's to say, that functions defined on an interval, let's say AB, t a value in AB, and taking their values u of t, which we frequently consider the position vectors in three-dimensional space. This will tend to describe a curve, although there are other vector value functions besides the position vectors. So that if we've got u of t, and this thing is going to be a triple. u1 of t, u2 of t, and u3 of t. If we've got a function such as this, we also want to define the derivative u prime of t, and this of course is going to be u1 prime of t, u2 prime of t, u3 prime of t. Right? This isn't really the definition. The definition is that this is the limit as h approaches 0, u of t plus h minus u of t divided by h, right? But then this is going to be what you'd get if you took u1 of t plus h minus u of t over u1 of t over h, and took the limits in each of the coordinates, and so this is the definition, and this is the result. Namely, the derivative is given by each of the derivatives in the coordinate functions. Now, the derivative satisfies a couple of rules. We'll present a couple of them right here. Namely, if we take a constant times u of t, we take the derivative of this. This derivative is equal to constant. So this is the function constant times u. It's the constant times the derivative of u of t. Similarly, if we've got b of t equals to b1 of t, b2 of t, b3 of t, right? Then we can look at the dot product of u and v. So this is a real valued function of t given by u1 of t, b1 of t, plus u2 of t, b2 of t, plus u3 of t, b3 of t. As I say, at each point t, it's the dot product of u1 of t, right, u of t with v of t. Right? Now, a rule that holds for differentiation of the dot product is the following. The derivative of u dotted with v at t, right, is equal to the first times the derivative of the second plus the second times the derivative of the first. Well, this is for times, it's the dot product. So the derivative of u dotted with v is going to be u dotted with the derivative of v plus the derivative of u dotted with v. The fact that a constant times a vector has for its a vector valued function has for its derivative constant times the derivative is easy to check. Let's check that this is the case. Right? So if we take u dotted with v, this is it right here. The derivative of u dotted with v at t, this is a product, another product, another product. So it's going to be equals to u1 of t times the derivative of v1 of t plus the derivative of u1 of t times v1 of t plus, oh, these u's here are not vectors, huh? Nor are these. These are the scalar parts, the component functions. Right? So it's going to be this plus now the derivative of u 2 times v2, which is going to be the first times the derivative of the second plus the second times the derivative of the first, u2 prime of t v2 of t, plus the derivative of u3 v3 is going to be the first u3 of t v3 prime of t plus u3 prime of t times v3 of t. Okay. So this is the derivative of the dot product. Now how about this formula right here? Is this equals to u of t dotted with v prime plus u prime dotted with v? Well, u of t dotted with v prime is going to be u1 of t v1 prime of t plus u2 of t v2 prime of t plus u3 of t v3 prime of t. We got u of t with v prime. And u prime of t dotted with v of t is going to be equal to u1 prime of t v1 of t plus u2 prime of t v2 of t plus u3 prime of t v3 of t. And so now what we want to know is this equal to the sum of these two. Well, here we've got u1 v1 prime. Here we've got u1 v1 prime. Here we've got u1 prime v1. Here we've got u1 prime v1. u2 v2 prime, u2 v2 prime, u2 prime v2, u2 prime v2, u v3 prime, u v3 prime, and u prime v3, u prime v3. So the answer is yes. The derivative of the dot product is given by the first dotted with the derivative of the second plus the second dotted with the derivative of the first. We next want to consider several rules which are natural for combinations of vector value functions. In particular, if we've got u of t equals to u1 of t, u2 of t, u3 of t. Now we wish to make a change of variables here. That's to say, if we let t be some function of s, then we can write u of s is u1 of f of s, f of t, u1 of f of s. F of s gives us t, and now we have u1 of t, u2 of f of s, u3 of f of s. Now if we wish the derivative of u with respect to s, u prime of s, or if you want derivative with respect to s, u of s. This is going to be equals to, we wish to differentiate this with respect to s here. So this is going to be equals to, this is a composition, so it's the derivative of u1 at s, f of s times the derivative of f at s. That's the first component. The second one is derivative of u2 at f of s times f prime at s. And the third component is the derivative of u3 at f of s times f prime of s. And this multiplication here now is just strictly multiplication. Huh? And so now, each of these terms has got f prime of s in it, so we can bring that out and write this as f prime of s, derivative of u1 at f of s, derivative of u2 at f of s, this is equals to, this is the vector valued function u prime at f of s. So this is u prime at f of s times f prime at s, where this is scalar multiplication. Now this, of course, is similar to composition for real valued functions. That's to say, the derivative of f of g of x is equal to the derivative of f at g of x times the derivative of g at x. Right? Here the derivative of u of f of s is the derivative of u at f of s times the derivative of f at s. So this is a very natural thing and will be made use of. Right? Second thing holds here as follows. Suppose we've got a second vector valued function, v, v of t equals to, say, v1 of t, v2 of t, v3 of t. We now want to take a look at the cross product of u of t and v of t. We wish to differentiate this. Now this is going to be a vector valued function, and the formula that we're going to get here is that the derivative of this cross product is going to be equals to the first crossed with the derivative of the second plus the derivative of the first crossed with the second. So you've got a natural rule for the cross product. The derivative of u cross v is u crossed with the derivative of v plus the derivative of v cross, derivative of u crossed with v. Now the order in which you do this is important, of course, because if you commute the cross product, you get the negative of what you have if you have it in its usual order. We want to check and make sure that this is the case. Right? So we've got u cross v. Let's look at what that is. Oh, u cross v of t. Right? This is going to be what? It's going to have a first component, second component, third component. The first component is going to be u2v3 times v3 minus u3v2. The second component is going to be u3v1 minus u1v3. And the third component is going to be u1v2 minus u2v1, v2 of t, v1 of t. So there's the cross product of u with v. Now it's derivative. All right? The derivative of u crossed with v. There's a product here, so we have to use the product rule on this. What we're going to get is u2 v3 prime, right, plus u2 prime v3. Right? We're going to get minus u3 v2 prime minus u3 prime of t, of course, v2 of t. Right? That's the first component. The second one is going to be u3 of t, v1 prime of t, plus u3 prime of t, v1 of t, minus u1 of t, v3 prime of t, and minus u2 1 prime of t v3 of t. Right? That's the second y component, if you want here. And the z is going to be u1 of t v2 prime of t minus or plus u1 prime of t v2 of t minus u2 of t v1 prime of t and minus u2 prime of t v1 of t. Okay, so this is the derivative of u crossed with v. And now the claim is that it's u crossed with the derivative of v. Well, u crossed with the derivative of v is going to read exactly like this, except that there will be a derivative of v here, so that we should be able to find u2 v3 prime here. There it is. Minus u3 v2 prime. Minus u3 v2 prime. Right? That's going to be the x component of u crossed with v prime. The y component is going to have u3 v1 prime, that's here, minus u1 v3 prime, that's here. And the z component is going to have u1 v2 prime minus u2 v1 prime. Right? So that's u crossed with v prime. Now u prime crossed with v. Right? That's going to be read the same as this, except that the u's will be u primes. So we should have u2 prime v3, that's there, minus u3 prime v2, which is there. For the y component, u3 prime v1 minus u1 prime v3. And finally, for the z component, u1 prime v2 minus u2 prime v1. And so you can see that the cross product, the derivative of the cross product, is exactly equal to the first crossed with the derivative of the second plus the derivative of the first crossed with the second. So it's two rules here that are very convenient for differentiating vector value functions. If we now take a vector value function r of t, this is designating the position in three-dimensional space. What we end up describing here is some sort of motion. If we think of t as time, where t is in an interval ab, where this is r of a is this vector over here, and r of b is this vector over here. And what we're dealing with then is, you can think of this as some sort of motion from this point along the curve over to here. So that you can write r of t as x of t, y of t, z of t, or sometimes, of course, we will just as easily write this as x of ti plus y of tj plus z of tk, where I, j, and k are the three unit vectors in the x, y, and z direction. Okay, then v of t, as in the plane, is found to be the derivative of r of t, and this is going to be x prime of t, y prime of t, z prime of t, and it's going to be a vector at each point t, which it points in the direction of the tangent, of the natural tangent, or the direction of this curve. Right? If we took r of t, we took it at a later point, r of t plus h, subtracted the two, we're going to get a small vector like this, and as h gets small, the resulting limit is going to result in it's going to be a vector in the direction of the motion of the movement of r of t. Right? And if we wish to calculate the length of this curve, what we wish to do is to, as before, partition the interval from A to B, like so. And if this is ti minus 1 and ti, 2 points in the partition, these are going to correspond to 2 points up here. Right? And the length between those two is going to be given by square root x of ti minus x of ti minus 1 squared plus y of ti minus y of ti minus 1 squared plus z of ti minus z of ti minus 1 squared. So this square root is going to give you this length, the straight line length here. Okay? Now if we wished to get the length of the curve, what we would want to do is sum this up across the partition and take the limit as the norm of the partition got small. Now what we do is we divide inside here by ti minus 1 squared. Likewise here, squared, and here, ti minus 1 squared. Right? To correct for that, what we should do is we should multiply outside of the square root by delta ti. That's to say delta ti is ti minus 1. Now this is going to correspond to the limit as the norm of the partition goes to 0. Sum I goes from 1 through n. By the mean value theorem here, there's some point between ti and ti minus 1, so this is equal to x prime at that point. Let's say at u I. So this is going to be equal to its squared plus y prime at some point in between vi squared plus z prime at some point in between wi squared, and outside here we still have delta ti. Right? Well, if x, y, and z are continuous, then replacing these by a single point will not change the value in here by much, nor will it change the sum. That takes some proving, but it can be shown. And so that this then is equals to the integral from a to b of the square root x prime of t squared plus y prime of t squared plus z prime of t squared dt. If we want just the length up to a point tau here, instead of all the way to b, this length, this s of tau, s is frequently used for distance, perhaps because the letter b is used so much for differentiation. Some alternate letter is needed for distance here to not confuse things. At any rate, this is the distance between a and tau here along the curve. So this might be r of tau here. This is this running distance now. Right? And then a thing that you can note here is by the fundamental theorem of calculus, the derivative of s at a point t is going to be the square root of x prime of t squared plus y prime of t squared plus z prime of t squared. So that the derivative of the distance traversed is this quantity right here. But you can notice that this is also the magnitude of the velocity. So this is the magnitude of v of t, right? Which is sometimes just written as v of t with no vector sign. So that the vector v of t then is a vector which points to the direction of the curve and whose magnitude is the speed or velocity. It's the speed at which the curve is being traversed. So that this vector points in this direction here and has the speed as its magnitude. Now, besides the velocity, the acceleration function, vector value function acceleration is defined to be the derivative of the velocity. Right? Now, what one can also do with this type of thing here is one can go backwards. That's to say, if you know the acceleration, you can find the velocity. If you know the velocity at a particular point, you know the velocity, you can find the position. If we've got a vector value function u of t, the antiderivative of u of t with respect to t is defined to be the antiderivative of u1 of t, that's in the first coordinates, antiderivative of u2 of t in the second coordinates, the antiderivative of u3 of t in the third coordinates. But now, instead of one constant of antidifferentiation, you need three. That's to say, you take this antiderivative plus any constant c, that's the first coordinate, this one plus any constant d, that's the second coordinate, this one plus any constant e, this will give you the third coordinate. And what this is then is this is a vector value function. Actually, there's a bunch of them with constants involved here, whose derivative is this given one right here. Right? Because the derivative in the first component here is the first component of u. In the second, it's the second, and in the third, it is the third. So you can anti-differentiate like this. The only thing you have to be careful with is that you need to put three constants of anti-differentiation if you anti-differentiate a vector value function. This will allow you to go back from acceleration to velocity if you know the velocity at a fixed time, because you can then determine what these constants are. Let's take a look at a specific type of motion here, in particular, well, it's spiraling motion. It begins down here on the x-axis and spirals upwards like so. Right? Staying in a circular cylinder and moving upward in the positive z direction. Such motion has an equation r of t given as follows. R of t is equal to r cosine 2 pi omega t, r sine 2 pi omega t, kt. Where omega here is in revolutions per unit time. So that when t is equals to 1, or if omega is equals to 1, then when t goes from 0 to 1, one complete revolution will be affected here in the x and y coordinates. The kt indicates that with k greater than 0, that this is motion as time progresses, the z coordinate increases, z equal to kt. Let's take a look at a specific example. Let's let r of t be equals to 2 cosine t, 2 sine t, 3t, let's say. Right? Now what happens here? As t goes between 0 and 2 pi, so this is t equals 0 here, and when t is equal to 2 pi, one complete revolution has been made here, and the height is 6 pi higher here. And so this is not to scale, but nonetheless indicative of what happens here. This is r of t. Let's look at b of t. Okay, this is going to be 2, derivative of cosine is minus sine. Y coordinate is going to be 2 cosine of t, and the z coordinate is going to be 3. Okay, the magnitude of v of t going to be s prime of t. The speed is going to be the square root of 4 sine squared t plus 4 cosine squared t plus 9. Since sine squared plus cosine squared is equal to 1, this is the square root of 13. So what this indicates is that the spiral motion here is taking place with a constant velocity of square root of 13. Let's take a look at the acceleration. This is the derivative of the velocity function, which is going to be equals to minus 2. Derivative of sine is cosine, so cosine of t minus 2 sine of t, derivative of 3 is 0. So what this indicates is what? That this is equals to minus 2 times r of t. R of t was, well, not quite. Right? It's equals to minus 2 times cosine t sine t 0. This indicates that there's no acceleration in the upward direction here. The upward velocity is a constant. This, however, is a vector at each point here that points directly in toward the z-axis with no k components. Right? So this is a of t. Right? The acceleration for this motion is completely directed towards the z, in the z direction. Now, one thing to note with respect to acceleration. Right? There are generally going to be two parts to acceleration. One is the increase in the speed along the curve, and the other one is the part of the acceleration that is directed in the direction in which the curve is curving or turning. Now, while the derivative of the position is the velocity, the magnitude of the velocity is the speed, the derivative of the acceleration, the magnitude of the acceleration is not in general going to be equal to the derivative of the speed. It's not in general going to be equal to it. However, the rate at which the speed is changing is going to determine one part of the velocity in the direction of the curve. The other part is separate, and it's going to add to the magnitude of the acceleration here. So that here, for example, the speed is the square root of 13. The derivative of the speed is 0 in this case. Right? The acceleration, however, has a magnitude of 2. So, the spiral, the velocity, the speed around the spiral, which is the magnitude of the velocity, and the acceleration, which is a vector pointing inward at all times toward the z-axis. We wish to consider r of t describing motion again here in three-dimensional space. Perhaps something like this. And this then is r of t is given times t. B of t points in the direction of the motion. V of t is given by the derivative of r of t. And what we want to do is we want to consider putting a coordinate system right here at the point r of t with a unit vector in the direction of v of t, so that t of t, the tangent vector, unit tangent vector, t of t can be determined by taking v of t and dividing by the magnitude of v of t. This will result in a vector that has got a unit length t of t at each point on the curve. So we've got a unit tangent vector here at each point on the curve, pointing in the direction of the motion. Okay, so that's t of t. Now, the thing to know is this. If we take t of t and dot it with itself, since this is a unit vector, then we're going to get the magnitude of the vector, which is 1. Now, if we differentiate both sides of this, right, we get the t of t dotted with the derivative of t of t, right, plus the t of t dotted with the derivative of t of t, or let's say 2 t of t dotted with the derivative of t of t is equal to 0. So that's it. The derivative of t of t is perpendicular to t of t. We're going to use it to get a second vector here, which we're going to call n of t, right? The unit normal vector. We'll see that n of t points in the direction in which this curve curves, and for that matter, that the acceleration of r of t takes place completely in the plane determined by t of t and n of t. Right? N of t is going to be gotten by taking the derivative of t of t and dividing by its magnitude. This will give us a unit vector, right, perpendicular to t of t. So here we have got this vector n of t. Okay? And the acceleration takes place in the plane, as we'll see, determined by t of t and n of t. Sometimes it's useful to have a third vector here. This is called a binormal vector, the unit binormal vector. It's the second normal vector, so binormal. It's written as b of t, and it's equal to the cross product of t of t and n of t. The cross product of t with n, since these are perpendicular, is going to be a vector that's perpendicular to each, and since these have a unit magnitude, this vector here is also going to have a unit magnitude. So you can get a third vector here and form a coordinate system, Tn and b here. All right. In this fashion, the t of t and n of t are going to be the most important because of this fact right here, that the acceleration is in the plane determined by them. But they're our unit tangent and normal vectors. I'll take a look at a specific example of tangent and normal vectors, and this example should indicate that even if you start with fairly simple motion, these vectors are not necessarily all that simple, and that the information that they contain summarizes something that's perhaps somewhat complicated. Let's take a look at what it looks like to be some fairly simple motion here. Let's let r of t be equals to, well, let's say t squared, t cubed. And with t between 0 and 1. So that this motion starts out at 0, and ends up at the corner of the unit cube and increases in all three coordinates. It stays within the unit cube here. It starts at this corner and ends up at this corner. Let's look at v of t. It's equals to 1, 2t, 3t squared. I guess this indicates that this motion sort of proceeds along the x-axis here at the start. That's to say that when t is equal to 0, the velocity vector is 1 in the x direction, but 0 in both y and z. So the picture can be drawn something like this. The magnitude of v of t is equal to the square root of 1 plus 4t squared plus 9t to the fourth. Right. So we now have our r of t. We've got v of t. And now we can get t of t by taking v of t over the magnitude of t of t. So t of t is equals to, well, 1, 2t, 3t squared over the square root of 1 plus 4t squared plus 9t to the fourth. That's to say, this vector has for its first component 1 over this square root, for its second 2t over the square root, and for the third 3t over the square root. This is scalar multiplication of that vector. All right? Now, to find n of t, we first of all want to find t prime of t. Okay? Now, in each component here, we've got a quotient. All right? So, in the x component here, we've got 1 over this. Right? I guess what I wish to do here is to simplify this rather than getting a messy derivative here, is to use the quotient rule here on this. That's to say, the derivative of this should be the denominator, square root 1 plus 4t squared plus 9t to the fourth, times the derivative of the numerator, which is 0, 2, 6t, minus the numerator, 1, 2t, 3t squared, times the derivative of the denominator, which is going to be 1/2, this to the minus 1/2, 1 plus 4t squared plus 9t to the fourth to the minus 1/2, times its derivative, which is going to be 8t plus 36t cubed. So this is times 8t plus 36t cubed, all divided by the denominator squared. 1 plus 4t squared plus 9t to the fourth. Right? Squared. Right. What one can do is check that in each coordinate, this is what we should have. That's to say, we've got the denominator times the derivative of the numerator, which is 0, minus the numerator, which is 1, times the derivative of the denominator, which is 1/2 this to the minus 1/2 times that quantity right there over the denominator squared, so that in the x coordinate, we've got the right quantity here. So this is t prime of t. Now the next thing we need to do is to get n of t, is to compute t prime of t divided by the magnitude of t prime of t. The magnitude of t prime of t is clearly going to be a bit messy here. We're going to want to take the x, y, and z coordinate functions here, square them, and take the square root. Right? So that this notation for n of t hides the fact that the actual computations may be messy. Note, though, this is r of t, this is v of t. You can compute a of t very simply here. It's equals to 0, 2, 6t. And so these three things are fairly simple here. However, you frequently wish to write the acceleration in terms of the normal vector vector and the tangent vector, and that's not going to necessarily be that elegant. We then want to consider a concept which is called curvature, and to do this we're going to go back to vector value functions in the plane, and where the concept of curvature is simpler. And the idea is basically this. If you go around a small circle at a constant rate, you continually curve toward the center, and so a small circle should have large curvature as compared to a larger circle. If you try and traverse a larger circle at a constant rate, right, the circle doesn't curve as much, and so that a larger circle should have smaller curvature. All right. If we've got some r of t in the plane here, what we wish to do is the following. We wish to consider this angle phi right here that is made with the tangent vector. Recall that t of t is equals to v of t over magnitude v of t, right? Where r of t is any vector value function describing this curve. What we really wish to do is we wish to reparameterize this curve here so that we are traversing it at a constant unit rate. Reparameterize it with r of s. This can be done as follows. If this curve here is described for t between a and b, then the distance traveled, s, starts out at 0 at a and is an increasing function until you get to b. Right? So from 0 to the length of the curve. It's an increasing function, and consequently it's got an inverse, so that if this is s of t, we could then talk about t of s for a given value s here. Right? For each s, we've got a t of s. If we reparameterize this instead of r of t, we look at r of t of s, it's an easy calculation to show that the magnitude of the velocity in this case is going to be equal to 1. Okay. At any rate, we will presume then that we're looking at r of t or r of s here that traverses this at a unit rate. So that in particular, if this is going to be at a unit rate, then the unit tangent vector and the unit is going to be the same as the velocity vector. The normal vector is going to be over here like so. The tangent vector is going to be equal to the velocity vector if this is done at a unit rate, because the magnitude of the velocity will be 1. Okay, we want to write t then in terms of this angle phi. T is equal to cosine of phi I plus sine of phi j, where phi and t are functions of s. If you want, we could put s in here. Cosine phi of si, sine phi of s j. So what we get here is that then dt ds is going to be equal to minus the sine phi of s times phi prime of s I plus the cosine phi of s times phi prime of s j. curvature, right, is going to be the magnitude of d phi ds. Right? But if we take the magnitude of both sides here, we find that the magnitude of dt ds is equals to the magnitude over on this side here, which is going to be the magnitude of phi prime of the absolute value of phi prime of s, right? The curvature absolute value here of d phi ds, rate of change of phi with respect to s, times the magnitude of cosine phi I, sine phi I minus sine phi I plus cosine phi j, which is going to be 1. So that we get the magnitude of the derivative of t with respect to s is going to be phi prime of s. Now, changing things around here so that you've got a unit speed is not particularly convenient. However, what we can do with this from the computational standpoint is, instead of computing phi prime of s, we're going to compute the magnitude of dt ds, but the magnitude of dt ds, by the chain rule, is the magnitude of dt derivative tangent vector with respect to time divided by ds dt. Right? That's to say, dt ds times ds dt is dt dt. Right? So, from a computational standpoint, this will be the curvature at times t, no matter what parameterization is given. That's to say, if we start out with r of t, right, we can compute t of t, dt dt, and ds dt, which is the magnitude of the velocity, right? So that if you want here, we could write this also as kappa of t is dt over the magnitude of v of t. Magnitude dt over v, magnitude of v of t, yeah? All right. In particular, we want to take a look at a circle of radius r and see what this gives for the curvature. So for a circle of radius r, we could let r of t be equals to r cosine t, r sine t. This will give us a circle of radius r, the parameterization of a circle of radius r. So that v of t is equals to minus r sine t, yeah, r cosine t, so derivative is going to be minus r sine t, times r, and the second coordinate is going to be r cosine t. Magnitude v of t, right, is r. So that this parameterization of the circle radius r has for its velocity r. Okay, so that t of t is v of t over magnitude v of t is going to be minus sine of t cosine of t. And t prime of t is going to be equals to, derivative of minus sine is minus cosine, the derivative of cosine is the sine, right? And so the magnitude of t prime of t is going to be equal to 1. Right? Square root of cosine squared plus sine squared, so it's going to be 1. So t prime of t over magnitude v of t is going to be 1 over r. So a circle of radius r has curvature kappa given by 1 over r, which agrees with the initial idea here, namely that the bigger the circle, the smaller the curvature should be. Traversing this at a unit rate of speed would result in greater sense curvature if the circle was small than it would if the circle was big. The curvature then for a circle is given by a reciprocal of the radius. In general, for any curve, the curvature is given by, at time t, dt dt, its magnitude, divided by the absolute, the s dt, or if you want, the magnitude of dt dt divided by the magnitude of the velocity at times t. Curvature now still in the plane. If we've got a curve defined by y is a function of t and x is a function of t, and it goes something like this, then this is a tangent vector here, right? And this is the angle phi. We want to reparameterize this curve, presumably here, with t of s, and in particular what we want is for the curvature kappa at any point t, it's going to be equals to d phi ds. And the way to compute this, of course, is to compute d phi dt and divide this by dt, well, to multiply it by dt ds or divide by ds dt. Let's consider this situation here now, where y is a function of t and x is a function of t. And then the things to note is phi is the angle whose tangent is y over x. So phi is tangent inverse of y over x. So that phi prime of t is going to be equals to the derivative of this. Now treating y as a function of t and x as a function of t. This is a composition, so the derivative is going to be 1 over derivative tangent inverse is 1 over 1 plus the quantity squared, so it's going to be 1 over 1 plus this should be dy dx. Right? V is the tangent inverse of dy dx, which is going to be tangent inverse dy dt over dx dt. So 1 over dy dt divided by dx dt, quantity squared, times the derivative of dy dt over dx dt, which is a quotient. Right? Derivative is the denominator. We can write this as x prime and y prime, so the derivative is the denominator. X prime times the derivative of the numerator, that's y double prime, minus the numerator, y prime, times the derivative of the denominator, x double prime, over the denominator squared. So this now is equals to, multiplying this out, now this is y prime and this is x prime, so this is going to be equals to x prime, y double prime, minus y prime, x double prime, over, multiplying through here we get x prime squared, and multiplying here we get plus y prime squared. Now this is where, this is phi prime of t. What we want is d phi ds, so that's to say what we want to do with this is we wish to divide this by ds dt. So ds dt is the square root of x prime squared plus y prime squared. So if we divide by this square root, we're going to get that this is going to be equal to this to the 3/2 power. So here then is the formula for the curvature when x and y are parameterized as functions of t. Right? Where the primes here all represent the derivative with respect to t. Okay. Now, in the event that y is a function of x, right? That's to say we can let x equals t and y equals f of t be the parameterization. Then, what? If x is equal to t, x prime is equal to 1, x double prime is equal to 0, the derivative with respect to the second derivative with respect to t. The first derivative with respect to t is going to be 1, the second derivative is going to be 0, and we can write y prime and y double prime, all right, as the derivative of f with respect to t and the second derivative. And so then for this situation here, x prime is 1, so in the numerator here we get y double prime. X double prime is 0, so that's all there is in the numerator. In the denominator we've got x prime, which is 1. Y prime is y prime, so plus y prime squared to the 3/2 power. This is kappa if y is a function of x. That's to say this is equals to f double prime of x over 1 plus f prime of x squared all to the 3/2 power. So this then is a formula for the curvature for a function of x. All right. We should make one slight correction here, and that is to put absolute values around the 3 prime. Absolute values here, so that we have absolute values in the numerator here. The denominator doesn't require them. And absolute values here. In the event that phi is if the curve is going the other direction, we want the curvature to be represented by the magnitude of the d phi ds. It's to say it's like so. So if you get a negative value for here, you take the absolute value, and this gives you the curvature. So here then are two formulas. One for the curvature of a curve given parametrically by y and x as functions of t, and the second one, the curvature for a function at a point x. Let's take a look at an example involving curvature and parametric equations. We call it the cycloid, as this equation describing it. X is equal to r theta minus r sine theta. That's x is a function of theta. And y is equal to r minus r cosine theta. Okay, this looks like so. And we can treat this as a function of t by simply replacing theta by its t here. So we have x of t is equal to r t minus r sine t, and y of t is equal to r minus r cosine t. And so these are the parametric equations. And now we call it that the curvature kappa is given by kappa of t is y double prime x prime minus x double prime y prime absolute value over x prime squared plus y prime squared to the 3/2 power. Okay. So what we need here are x prime and x double prime, y prime and y double prime. X prime of t is given by r minus r cosine t. X double prime of t is r sine of t. Yeah? Derivative of cosine is minus the sine, so we get r sine of t because of the minus sign. That's x double prime. Y prime is equals to, derivative of cosine is minus the sine, so this is going to be r sine t. And y double prime is r cosine t. Okay, now putting that into this formula here, we get the kappa of t is equals to r cosine t times x prime, which is r minus r cosine t, right, minus x double prime, r sine t, times y prime, which is r sine t, right. This is an absolute value divided by x prime squared plus y prime squared. That's to say r minus r cosine t, quantity squared, plus r sine t, quantity squared, and now we need all of this to the 3/2 power. Right. Okay, let's simplify this just a little bit. I'm going to get r squared cosine t minus r squared cosine squared t, right, minus r squared sine squared t. That's the numerator. In the denominator here I've got r squared minus 2r squared cosine t plus r squared cosine squared t plus r squared sine squared t. Okay, this is cosine squared plus sine squared, so that's 1. So I get r squared. Now this needs to be to the 3/2 power. So in the numerator here I get r squared cosine t minus 1. So r squared multiplying this throughout. In the denominator here I've also got r squared multiplying everything throughout. So I'm going to get r squared. Now what have we got here? Here we've got sine squared plus cosine squared, so that's 1. So this is going to give us 1r squared, and it's going to give us another r squared over here, so we've got 2r squared. And then we've got times 1 minus cosine t. And this is to the 3/2 power. The whole thing is. Okay, continuing to simplify here because it's going to shed some light on this hypoid. Otherwise, this is a perfectly good answer, of course, for the curvature. What do we have here? We've got this to an absolute value. We've got the numerator here in absolute value here. So this is 1 minus cosine t, absolute value. Absolute value of r squared, and we've got 2r squared to the 3/2 power here. So this is going to simplify some. We end up with 2 to the 3/2, so that's 2 square root of 2 in the denominator, first of all. Right? R squared to the 3/2, divide that into r to the 2 power is going to give us square root of r. Right? And now we've got minus cosine t to the 3/2, and cosine t minus 1 in absolute value, which is 1 minus cosine t. And so this is going to give us 1 minus cosine t to the minus 1/2 power. Okay. Let's just change this just slightly here. This is going to be equals to, we end up with square root of r over 2 square root of 2. And then we can simplify this just a little bit more by noting that 1 minus cosine t, right, over 2 is equals to sine squared of t over 2. So we can replace this 1 minus cosine t by sine squared of t over 2. When we take the square root, we're going to end up with sine of t over 2 right? And this is going to be to the minus 1 power. So here's a simplified form here for the curvature of the cycloid. And I guess the thing that you can notice from this is that the sine, when t is equals to pi, right? That's to say at the middle here, t equals pi, and the sine is going to be equal to 1, and that's going to make this quotient here, since this is sine to the minus 1, it's going to make this as large as possible so that the curvature is minimal. The curvature is minimal at the center. Right? And here's a formula for the curvature. It's been simplified considerably so that it can be computed real easily. The curvature is minimal at the center here, and the curvature is maximal at the two ends. Take a look now at the curvature of a curve, which is a function of x. And probably no better place to start here is that let y equal x squared. Then the curvature, kappa of x for y equal function of x is y double prime, magnitude y double prime, over 1 plus y prime squared to the 3/2 power, where y prime is f prime of x, and y is f of x. Y equals x squared, the parabola. Well, y prime is equals to 2x y double prime is 2. So the curvature is given by 2 over 1 plus 4x squared to the 3/2 power. So this gives the curvature for a parabola. Notice that perhaps that when x is equal to 0, the curvature is 2. And the curvature then is equal to the concavity when the derivative is 0. So if you can think of this curvature as being the same as concavity when the curvature occurs at a point where the curve is flat. All right, let's take a look at another example. Let's do y equals e to the x. Right. Then y prime is e to the x and y double prime is e to the x. And so that the curvature, as a function of x here, is going to be e to the x over 1 plus e to the x squared, or e to the 2x to the 3/2 power. Right. Well, y equals e to the x looks like this. It's perhaps curious here to ask the question, where is this curvature maximal? somewhere around here, there's a maximal curvature. This thing tends to be very flat in both of these directions. So if we want to determine whether the curvature of a curve is maximal, we do the natural thing here, namely we take the derivative of the curvature instead of equal to 0. So the derivative of the curvature is the denominator here. We've got 1 plus e to the 2x to the 3 halves times the derivative of the numerator, which is e to the x, minus the numerator, e to the x times the derivative of the denominator, which is 3 halves, 1 plus e to the 2x to the 1 half, times the derivative of 1 plus e to the 2x, which is 2 e to the 2x. Derivative of 1 is 0, derivative of e to the 2x is 2 e to the 2x, all divided by the denominator squared. So 1 plus e to the 2x to the 3 halves squared, or 1 plus e to the 2x cubed. We want to know when this is equal to 0. All right? When is this equal to 0? And so we don't have to concern ourselves with what happens in the denominator. This will be 0 when the numerator is 0. And we can also multiply this through here by 1 plus e to the 2x to the 1 half power. So we're going to get 1 plus e to the 2x, or divide through by it even better, right? Since it's positive. And we're going to get this to the 1 power times e to the x minus, we're dividing by this, so it's not going to be here when we're done. We're going to have minus e to the x times 3 halves times 2, which is times 3, times e to the 2x. Okay, this is to the 1 power here. So this is going to be equal to e to the x. We want to know when this is 0. It's equal to e to the x plus e to the 3x minus 3 e to the 3x. We can divide by e to the x here, since it's positive, and so this will be equal to 0 when 0 is equal to 1. This is minus 2 e to the 2x. After we've divided by e to the x, we're going to have plus 1 and minus 3, so minus 2 e to the 2x. That's to say, when e to the 2x is equal to a half, right? Or taking the logarithm, we get this is true when 2x is log of a half, right? That's to say when x is equals to, log of a half is minus the log of 2, so this is minus the log of 2 over 2. So that negative log 2 minus log 2 over 2, the curvature is maximum. Log 2 is about 0.7, so this is at about minus 0.35 is where the curvature is maximal here. Perhaps a place that would not be expected. At any rate, you can compute the curvature, and here in this case here, if you're interested, you can find out where it's maximal or where it's minimal. We now want to take a look at curvature in three-dimensional space. And so if we've got some sort of a curve here, given by r of t, t in the interval a to b, right? So this would perhaps be r of a, here's r of b up here. Right? Then what we wish to do here for the curvature at any point t, right, is we wish to recompute this curve here so that it's traversed with a unit speed, in which case we're going to have a new parameter, kappa of s, and the curvature at a point s along this curve here is going to be given by the derivative of the tangent vector at s. Now, that's actually not what we're going to compute. Here perhaps is the tangent vector. What we'll actually compute here is that t prime of s at a point t is given by t prime of t divided by s prime of t. Right? That's to say, s prime of t. We want the absolute value of this, of course, over here. The magnitude of this, of course, over here, the magnitude divided by s prime of t, so that kappa of t is going to be magnitude t prime of t over magnitude v of t. Right. Now, this is the analog to in the plane. In the plane, the derivative of t with respect to s is exactly the curvature kappa, and we call that 1 over that number kappa is the radius of curvature for the best circle approximating this. Let's take a look at this situation again here. Let's suppose this goes from A to B, so if this is A and this is B, then we have s of t here. Right? For each t, we've got exactly one s, and so for s here, we can define a function t of s, which takes a particular s back over here to the value of t of s. Right? It's the inverse of the function s of t. Right? If we now reparameterize r of t with s, so if we look at r of t of s, right? I simply wish to claim here that this has now been reparameterized so that this is a parameterization which traverses this curve at 1 unit length per unit time. That's to say at 1 unit of speed. To see that, let's take the derivative of this with respect to s. Right? This is going to be equal to the derivative of r at t of s, where this is the derivative now of r of t, right, times the derivative of t at s, which is going to be equals to, right, the derivative of r at t of s. The derivative of t at s is 1 over the derivative of s of t, so this is over s prime of t. And so, what is this? This is the derivative of r at a particular point t, where we're looking at t of s. So this is r prime at t over s prime at t. S prime of t is magnitude v of t. Huh? Right. So we find that the magnitude of this is 1. The magnitude of r prime of t over magnitude v of t is equal to 1, because what? Magnitude r prime of t is v of t. Right? So if we do this parameterization, the curve has been reparameterized so that it's traversed at 1 unit of speed. Right? However, as I mentioned, what we're going to really want to do is to use this to compute the curvature, or equivalently this. Okay. Having done this, then, we're going to want to talk about the radius of curvature, rho. It's going to be 1 over the curvature. Right? And recall, if you look at the normal vector n of t here, right? N of t is given by t prime of t over magnitude t prime of t. Right? And the center, let's designate the center of the best circle approximating this as c of t. It's going to be in the direction of n of t away from this point r of t. So c of t, the center of the circle, best approximating this curve, which might be here, for example, is going to be given by, go to r of t first of all, r of t, and then add on to that Now we can put this together with this fact here for kappa and get that this is equals to r of t, right, plus 1 over kappa of t is going to be v of t, magnitude v of t, over magnitude t prime of t. Right? But now n of t is t prime of t over magnitude t prime of t, so this is going to be t prime of t over magnitude t prime of t squared. Right? This is perhaps, however, the most useful formula here for, the most intuitive formula for finding the center of the best circle approximating this curve. Namely, you go to r of t, you take the radius of the circle that you want, 1 over kappa, and multiply that by the normal vector here, like so. That's giving you the point where the center of the best circle is located. Let's take a look at a specific example involving curvature. A spiral here. Certainly is simple enough. Just imagine we've got a spiral that goes up here like so. Right, starting on the x-axis here. And so we could write such a spiral as r of t is equals to, let's say, let's give this a circle of radius 3, so 3 cosine, say it's 2 to t, 3 sine of 2 to t, and let's say 4 to t. What we want to do is we want to compute the curvature, which we expect to be constant here, and we wish to compute the center of curvature, c of t, which we'll get by looking at r of t plus 1 over kappa n of t. So 1 over kappa of t n of t, this will give us the center of the curvature. So, we want r prime of t. It's going to be 6 here. Derivative of cosine is minus the sine, so it's going to be minus 6 sine 2 to t. Derivative of sine 2t is cosine 2t times 2, so 6 cosine 2t and 4 here, right? The magnitude of r prime, this of course is v. The magnitude of v of t is square root 6 squared, sine squared plus cosine squared is 1, plus 4 squared up. That's 36 square root of 52. Okay, so t of t is v of t over square root 52. Like so. So t prime of t is going to be what we get if we compute the derivative of v of t here and multiply by 1 over square root 52. That's derivative of v of t is minus 12 cosine 2 to t. Derivative of cosine is minus the sine, so it's going to be minus 12 sine of 2 to t and 0. The magnitude t prime of t is equals to square root of 12 squared up times 1 over square root of 52. So the magnitude of t prime of t is going to be 12 over square root 52. Okay? So this says that the curvature, kappa, as you'd expect here, is going to be magnitude t prime of t over magnitude v of t is going to be a constant. Expect the spiral here to have a constant curvature. And this constant is going to be 12 over square root 52 divided by square root 52, which is to say 12 over 52. Or I guess simplifying here, this is 3/13. Now the center of curvature now here for this is going to change as the spiral changes here, and it's going to be given by r of t, which is 3 cosine 2t, 3 sine 2t, and 4t, plus 1 over the curvature, that's to say plus 13 over 3 times n of t. N of t is t prime of t over magnitude t prime of t here, right? So n of t is going to be equals to t prime of t over magnitude t prime of t, which is going to be equals to 1 over square root 52 divided by square root 52 over 12, right, times this, minus 12 cosine 2t minus 12 sine 2t 0. So we're going to get here 13/3 times 1/12, right, times minus, well, I guess the 12th here is going to make this cosine 2t. So like so, cosine, the 12 here is going to make this, the square root of 52 is canceled, and 12 is going to make this minus cosine 2t sine of 2t 0. So combining these two here then gives you the center of the best circle approximating this curve. So that the circle here gives a good approximation to the direction along, the best approximation to the direction along the curve. That center is not going to be on the z-axis. It's easy to compute that it's not. There's the location of the center. So there's an example of a curve, this being with a spiral, and finding the curvature and the center of the circle of curvature. We're going to take a look again at the acceleration, which, as was mentioned before, occurs in a plane determined by the tangential vector and the normal vector. All the acceleration was planned to occur in that plane, and sometimes it's worthwhile writing the acceleration as having two components. The velocity is having two components. Well, the acceleration is having two components. Acceleration is not only a component of action in the direction of the tangent vector. The acceleration is having two components, one normal and one tangential. Right? To see what's happening here, let's write. Let's consider r of t first of all, and v of t. Right? Now we can write v of t as s prime of t times t of t, where t is the unit tangent vector. If we do this and differentiate here, now we get that a of t, the acceleration vector, is given by, this is the product here, well, it's a vector product, the scalar, so the derivative is going to be the first times the derivative of the second plus the second times the derivative of the first, or if you want s double prime of t, different derivative of s prime of t times t of t plus s prime of t times the derivative of t of t. is t prime of t over magnitude t prime of t. So you can write t prime of t here as n of t magnitude t prime of t. And this gives us this formula. S double prime of t times t of t, right, plus s prime of t times t magnitude t prime of t n of t. Right? And this shows then that the acceleration has got two components, a tangential part and a normal part. The rate of change of the velocity is the tangential part, and that's somewhat intuitive. The normal part is perhaps not so intuitive. It's worthwhile writing it a third way here also, and that is this. Since kappa, the curvature, is magnitude t prime of t over magnitude s prime of t, or magnitude v of t, we can write magnitude t prime of t as kappa of t. S prime of t is all we need here, right? As kappa of t s prime of t. So this becomes s prime of t squared kappa of t n of t plus the second derivative of s t of t, and this gives you the acceleration. Right? So the acceleration has got a tangential component and a normal component. Tangential is the derivative of the velocity, the magnitude of the velocity, and the normal component is the velocity squared times the curvature. Okay. If we write this as a of t as having a tangential component ht times t of t plus a normal component a sub n times n of t, right? It's sometimes preferable to have another way to compute the quantity a sub t, the tangential component, and the quantity a sub n. To get at this, let's take v and dot it with a of t. Right? If we take the velocity and dot it with a of t, where a of t, let's say, is given right here, we find that the velocity does not have a normal component, it only has a tangential component. So this is going to be equals to s double prime of t times the magnitude of v of t, yeah? Well, s double prime of t is a sub t, so we get s double prime of t is a sub t, so we get that a sub t is equals to v of t dotted with a of t divided by the magnitude of v of t. This is a very natural formula in the sense that, what, the tangential component is the component of the acceleration, the direction of the velocity. Yeah? So a dotted with this divided by the magnitude of the velocity. This gives us then a means of computing the tangential component by using this dot product. Let's take a look at v of t crossed with a of t. Using this formula here. Well, v of t has only a tangential component, so that this crossed with